Here's an outline of what we'd like to cover today. We're going to do a brief on centrifugal pump overview, causes of rotating equipment failure, causes of seal failures, mechanical seal overview, general geometry, unbalanced versus balanced, pressure versus bellows, component versus cartridge, and single versus dual. Here's a typical centrifugal pump orientation. If you recall from Jerry's first webinar, he talked about all of these different components. We're going to concentrate on the areas in green, which are highlighted by number 6 and number 7. Here's a typical centrifugal pump system. The arrows in red indicate display the flow characteristics. At point A, the suction, you start in with a low pressure and low velocity. As it enters through the impeller eye and into the impeller vanes, these increase the pressure and increase the velocity. As it passes through the volute, the pressure remains high, but then the velocity starts to slow. And then as it exits the discharge, you have higher pressure and lower velocity. The velocity at E and the velocity A are very close. The flow that goes into the pump has to be the flow that goes out of the pump. So GPMs in, GPMs out. What the pump does is imparts head, and it increases the energy of the pumped fluid. Here are some causes of rotating equipment failure. On the sealing device, you'll see that it makes up 69% of the failures. Some of the causes of sealing device failures are operational, mechanical, seal components, and system design. And we're going to talk a little bit more about those. Some common causes of operational failures. Well, you're not operating the pump at the best efficiency point. If you recall from, if you were able to attend the first webinar series, we talked about the pump curve. Pumps are designed in systems to operate in and around their best efficiency point. This is an optimal location for that pump to run. If you're outside of those regions, you can have some flow characteristic problems which will cause a seal failure. One of them is insufficient net positive suction head, NPSH. This causes a phenomenon known as cavitation. We're not really going to get into cavitation, it is in itself a topic, a webinar on its own. But know that if you don't have proper head into the pump, this will cause instability in the rotating assembly and cause a seal failure. Operating the pump dead-headed. Oftentimes, pump systems will be throttled somewhere in the system with a control valve. If, let's say, you have a system designed for 200 gallons per minute, but you need a requirement of 5 gallons a minute, you throttle down your control valve, this chokes off the pumps, which gives can simulate a dead-headed operation. This causes recirculation inside the pump case itself and builds up heat, again, causing a seal failure. Dry running. Sometimes this can be confusing to certain operators because you have a dry run situation on the mechanical seal, yet the pump was flooded. And they say, well, how can that be? Well, think of an orientation where the pump is vertically. The mechanical seal sits on top of the pump. If you don't have, as stated in the next topic, improper venting, if you don't vent the pump correctly, an air bubble can form and won't be able to evacuate the stuffing box chamber, and of course will fail the mechanical seal through a dry run situation. Lastly, low vapor margin. These are flashing fluids. Generally, hot hydrocarbons will flash in atmospheric conditions. So as the fluid film passes across the mechanical seal, it can flash at the atmospheric side and cause a failure. Another area that's probably more common in the state would be boiler feed situations where you have hot water at 250 or 280 degrees. That will also give you a flashing situation. Mechanical. Some common causes: shaft alignment, or better yet, misalignment, coupling balance, impeller balance, and pipe strain. Pipe strain is actually a kind of a hidden killer. You'll build up a pump, everything will be fine, you put it in the plant, and you have to use come-alongs to straighten out the pipe runs to get them to bolt up to the pump. This imparts a lot of strain into the pump itself and can cause some real havoc, wreak real havoc with a mechanical seal. A bad base is another form. Is it grouted properly? Do you have a soft foot? Is there any loose bolts? And of course, bearing issues. As the tolerance on the bearings wear out and open up, you'll have shaft movement. Again, leads to a mechanical seal failure. System designs. Common causes. Seal flush arrangement. Do you have the proper seal flush for the type of seal that you're in the system that you're operating in? Insufficient cooling. That, again, is indicative of a flushing problem. Dual systems require auxiliaries. The auxiliaries have barrier fluids. Is your auxiliary seal pot in the right location? Do you have the right instrumentation on it? Is it piped correctly? Those will all cause seal failures. The length of straight pipe at suction. On some of the older pump systems, especially if they were skid-mounted systems that came in as a package, a lot of times designers put an elbow, a 90-degree elbow, right at the suction. What this causes is a turbulent region just before it goes into the impeller eye. These eddies, if you will, like a stream, you can see turning eddies on a stream, these cause for instabilities in the rotating assembly. Again, cause a seal failure. And of course, your suction, your discharge, and your bypass piping. All of the piping that's associated to your system, your pumping system, if it's not engineered correctly or there's changes were made over the years, if that's not taken into consideration, that again can cause you some real headaches. And of course, seal components. Poor tribological pairing. What tribology is basically the study of friction. Poor pairing would be face combinations. Those can add to some seal failures. The seal face material quality, making sure you have the proper seal materials for the application that you're running. Secondary seals, which are the gaskets and O-rings, again, making sure that they're properly selected for heat and chemical attack. Springs and bellows. Springs can get plugged up and clogged. Bellows, if they're the wrong metallurgy, can get corroded. And face distortions from pressure or heat. A mechanical seal under great pressure will actually bow, and the profile will get all messed up, and that can cause a leak as well. Now, what is a mechanical seal? A mechanical seal is a device that is used to control leakage between a rotating shaft and a liquid or gas-filled vessel. Now, the key term here is controlled leakage. You may or may not have heard this term before, but all seals leak. They have to. You have to maintain a fluid film across the entire mechanical seal face. Now, the leakage that comes out into the atmospheric side is generally very, very, very low. A lot of times it's measured with a VOC meter, and it's in the parts per million. Now, here are some sealing classifications. Now, these are all different types of seals, not just mechanical seals, but all types of seals, from gaskets and sealants all the way to the mechanical seals that we're going to talk about. Mechanical seals fall under the axial seals, and the categories that are under axial seals are pusher, non-pusher, single, and double. Now, before mechanical seals were developed, the typical way to seal a pump was with packing. Packing was a fibrous material that was usually impregnated with some sort of lubricant like graphite, and cut into sections, stuffed down a stuffing chamber, stuffing box, and then a packing gland was then applied in the backside to tighten everything down. Now I'm going to show you with my cursor that right there, item in gray, that is the packing gland. One thing to note here is that packing is in direct contact with your shaft. Whether it's actually riding directly on the shaft or on a sleeve, it is in direct contact with the shaft, and therefore it will rob horsepower. Now, where exactly does the packing flush water go? Now, packing has to be lubricated because it is in contact with the shaft. Usually there's a lantern ring, like we saw in the slide before, where the flush water can be applied. That water has to leak into either the process or to atmosphere, and that's the way that it can lubricate and cool that shaft. Now here are some of the problems. If you have leakage into your process, this can cause contamination into the process, especially if you don't want water into your system. Also, if you have overspray or there's water on the floor, this can be an OSHA concern and also a housekeeping concern. And lastly, if you get water towards the bearings, they can get into the bearing box, contaminate the oil, which will eventually lead to a bearing failure. Now, water consumption is something that sometimes isn't quite understood. When using a PAC system, you actually have to have, if you have a leakage rate or a seal flush going directly into the packing, you're going to consume a certain amount of water per year. So I've got a little bit of homework for everyone out there. If you were to take down 1 gallon per minute equals 525,600 gallons per year, and if you have any PAC systems at your plant, go out and try to find out how much water in gallons per minute you're actually using in that pump. Then go to your accounts payable people or someone who's paying that water bill, especially if it's city water, and see how much money you're actually spending per year. Packing may be an inexpensive way to fix a pump, but you may be, in the long run, a mechanical seal might be the option. You'd be surprised how much water you actually use. A mechanical seal overview. We're going to talk a little bit about the general geometry, unbalanced versus balanced, pusher versus metal bellows, and elastomer bellows, component versus cartridge, and single and dual seals. Now here are the main components, parts that make up a mechanical seal. You'll see that there's a stationary assembly in item number 1. There's a rotating assembly, item number 2. There has to be some sort of spring, which applies a closing force, and of course, O-rings and gaskets that seal all of the adaptive hardware. Some typical mechanical seal terminology. You can see there's the springs, the rotor and the stator, the anti-rotation pin, which holds everything together, the gland, which I mentioned earlier as adaptive hardware. The gland allows you to bolt your seal to your pump. Also, you can see the other parts of the mechanical seal here are the wear nose. The wear nose is always on the softer of the two face combinations. So if you have a silicon carbide versus carbon seal combination, the wear nose will be on the carbon. Also, you'll see that there's a dynamic secondary seal or a dynamic O-ring. We'll get a little bit more into this, but note that there's a spring and an O-ring. These are pusher-style seals, and we'll talk a little bit more about it, but I want you to note that the dynamic secondary seal. Mechanical seal leak points. Anywhere there's a gasket or O-ring, there could be a leak point. As you can see, items number 3 and items number 4. Item number 3 is the dynamic O-ring. Now that O-ring is called dynamic because it actually moves with the mechanical seal. It tracks with the springs. When it tracks with the springs, there's a possibility that it can erode, wear, fret, and then you get a leak. And of course, in between the two mechanical seals, if you have dirts, contaminants, off-design operation, these can all wear the seal, and then you'll get a leak. Now here's a couple of different classifications of mechanical seal. We're going to talk about the single seals, both inside and outside. Typical single inside pusher seals. Okay, the faces must be in contact. Faces must be flat to within 3 light bands, and most are 1 light band. And well, what exactly are light bands? Well, it's 34.8 millionths of an inch. Now, to talk a little bit about flatness and exactly what does flatness mean. If you could picture yourself standing in a big concrete floor, and next to you have, let's say, like a laser level. And off in the distance, someone's out there with a measuring device, some sort of a meter, a yardstick. And they're out there going around taking measurements, reading off of the laser level. You'll notice that there's differences in elevation in the topography. They could be 1, 2, 3, 4 inches, and that basically tells you what the valleys and peaks are on that floor. Well, if you were to shrink yourself down and put yourself on a mechanical seal and did the same type of readings, that would be, those differences in elevation could be no more than 34.8 millionths of an inch. And that is what's meant by flatness. Also, the faces must be lubricated by the liquid in the stuffing box for any single seal. Now here's an outside seal design. Again, all they've done is taken the rotating part, which is, you can see the seal faces in yellow as it runs up against the orange stationary face. They're outside of the process. Now you do this if, let's say, the stuffing box clearance isn't big enough for an actual mechanical seal. You have to mount it outside. Also, if you have lots of dirt and grit and contaminants, they can plug the seal. They can plug up the springs, again causing a failure. Also, if you had some highly corrosive material and you wanted to keep some of your metal parts out of that corrosive material, again, you would want an outside seal. Now we'll talk a little bit about multiple seals. Dual seals. These are both pressurized and unpressurized in the different orientations of back-to-back and face-to-face. Here's an inside back-to-back seal. Now the rotating element, you'll see are the two yellow faces, and there's a spring in the middle, and those seals are back-to-back. They're pushing up against the stators, and as the shaft rotates, they run in tandem to seal the system. Now, with any double seal or dual seal, you have to have a barrier fluid. Now, this orientation that you see here, everything in blue is the barrier fluid. You can see where there's a sealing liquid inlet and a sealing liquid outlet. All dual mechanical seals require some sort of fluid in that barrier chamber area. That fluid is generally used to collect leaked process stuff from the process. Could be anything that's like a gas of some sort, and then needs to be vented out to the seal pot, and then it's vented to flare. Or if it's pressurized, it provides lubrication to the seal faces, especially if the pumped fluid is overly dirty or it does not have very good lubricating properties. Now here's a dual unpressurized seal. Now I left the term tandem in there. Some of the old nomenclature from years back were to call tandem seals unpressurized and double seals pressurized. Today, the terminology is dual unpressurized or dual pressurized. It's much easier to just look at your system and say, well, is my barrier system under pressure? I have a pressurized system. If it's not, I have an unpressurized system. It makes it a lot easier than try to figure out and remember what's tandem, what's double, and all that. This is a typical orientation of a unpressurized dual seal. Now we're going to talk a little bit about balance versus unbalance, multiple spring versus single spring. Okay, an unbalanced seal. Unbalanced seals are the simplest designs. These are seals that you'll see used in internally sealed devices, internally sealed pumps. Something like a dishwasher or a washing machine will have an unbalanced mechanical seal in it. The process pressure in the seal chamber creates high closing forces on the seal. These have reduced pressure capabilities. An unbalanced seal. This is the orientation of an unbalanced seal. Now the equation for an unbalanced seal and the equation for a balanced seal, as you can see on top, the closing force of the springs plus the closing force of all other factors minus the opening force equals your net force. If you look at the seal itself, and I'll try to see if I can cursor over, but where the springs are located, which is item K, If you were to draw a line straight through that spring, you'll notice that the springs are directly in line with the interaction of the two mechanical seals, the two seal faces, the one in yellow and the one in brown. That is indicative of an unbalanced design. The seal chamber pressure also acts to open these two faces and provide you with the lubrication needed to operate the mechanical seal. It starts out at a higher pressure in the seal chamber, and then as it goes to a lower pressure in the as it approaches atmospheric side. A balance seal balances out a portion of hydraulic loads from the pumped liquid pressure. It reduces the closing forces on the seals and has increased pressure capabilities. Balance seals allow you to engineer the leakage that's really desired. They can be applied to a wide range, and they're the most common in a lot of API applications and ANSI applications that are out there. More of your high-end pumps will all have balance seals. Again, here's the equation and the orientation of a balanced seal. Now, you'll see the difference here. Again, if you follow my cursor, it goes through the spring at point at K, continues on, and you'll notice now that the inline force of the spring is above where the actual mechanical seals touch. This region down here, which is in blue as it interacts to the yellow seal face, is referred to as the balance shoulder. So as you're looking at any mechanical seal, and if you see the springs in line with the face, you know you have an unbalanced seal. If you see that it's above, you know you have a balanced seal. Now we're going to talk about the differences between a pusher and a non-pusher. Pusher seals. Okay. Again, going back to that dynamic secondary sealing area, the dynamic O-ring. Anytime you have a mechanical seal that has a spring of any sort, multiple springs, single springs, leaf springs, wave springs, it doesn't matter. If it has that combination with a dynamic secondary seal, a dynamic O-ring, that is a pusher seal. Pusher seals are one of the most common. Now, some of the pusher seal design limitations. Okay. Because you have a dynamic secondary seal, which is riding on a shaft, if you're using in a system that may have some, you get some leakage off of the seal face, that stuff has dirts and contaminants. If it's high heat, it'll coke up. Those are the items that you see here in brown. They'll build up underneath the seal, and they'll hang up that dynamic O-ring. These are really problematic in vertical applications, especially if you have a hot hydrocarbon in a vertical application. You'll get some coking on the inside, and it can plug up that dynamic seal in a hurry. Now, a metal bellows. Metal bellows provide spring force closure. Now, a metal bellows looks like an accordion. It's a set of metal rings that are all welded together to form what looks like an accordion. The bellows separate the process fluids from the atmosphere. The bellows metallurgy must be compatible with the pump fluid, and they work excellent in high temperature applications. Now this slide shows you, if you look directly underneath underneath the mechanical seal, you'll see that pile of dirt and contaminant. What you don't see is a dynamic O-ring. And that's the difference between a pusher seal and a non-pusher seal. Metal bellows are non-pusher seals. So if you don't see a dynamic O-ring, that is a non-pusher seal and has to be some sort of bellows. It eliminates that need for that secondary gasket. Elastomer bellows. This is a variation of the two. The elastomer bellows they're a pusher seal. They are a variation of pusher seal. You have the coil springs, which apply the closing force. And then you have an elastomer boot. The elastomer boot, again, separates the process fluid from the atmosphere. And it is limited to the temperatures and chemical compatibility. What elastomer bellows allow you to do is they're a little bit more forgiving to movement than a regular dynamic O-ring on a pusher seal. Elastomer bellows allow for a little bit more axial or radial movement. You'll see these in general service seals. Now we're going to talk a little bit about flexible rotors and flexible stators. Now, typical mechanical seals have a flexible rotor. It's the most common design. You'll see here where as the seal tracks right or left, the springs and the dynamic O-rings will work together to make sure you have contact with your other stationary face. Now, a flexible stator basically reverses the same process. The springs are now held stationary, and only the rotating face is fixed. These work well in vertical applications because a lot of times you'll have perpendicularity problems. The shaft will not be directly true to the perpendicular to the pump itself. If these things are tilted, these can take up a lot of that I guess off-tolerance operation, where if you had a flexible rotor, you would actually get a kind of a wobbling effect, and that would cause a seal failure in a very short time. The ISC2 mechanical seal uses a flexible stator design. And of course, now we're going to talk about cartridge versus non-cartridge seals. This is one of the more important sections on this seminar. One of the biggest things between the two we'll talk about here in a second. A component seal. They're generally less expensive, and that's one of the reasons because you are actually only buying the seal elements. You're basically buying what's in green, what's in yellow, and what's in orange. Those parts are basically swapped out into the pump, and you use the existing gland that came with the pump. They must be installed in individual pieces. There is a huge potential for assembly errors. A lot of times, sometimes depending on the technician, they may or may not know to touch the faces. They may apply lubricants to the faces, which is not recommended on certain applications. The other part is you have to manually set the axial locations of the components. Now, what that is, and hopefully this comes up. See if I can get it to come up. I had a nice. There it goes. Okay, right there, from the stuffing box face or the case of the pump to somewhere in the along the shaft. That distance is your setting distance, also known as, sometimes some people refer to it as seal crush. That setting distance has to be manually scribed on the shaft, manually set. One of the common problems that you see with component seal designs is the pump will be 20, 25, 30 years old. Has an O&M manual with it, and the O&M manual says to set the seal at this distance. Well, that was for a seal company that may or may not be in business anymore. The replacement seal that is sent in may have information that conflicts with what's in the manual, and there's some confusion as to actually how you should set the component seal. If you do not set that component seal correctly, you're either going to overheat the seal because you have too much compression, or it's going to leak because it's undercompressed. How do you get around that? Very simple. Cartridge seal designs. Cartridge seal designs are a seal in a package. They are slightly more expensive than a component seal because they come with two additional parts. They come with a sleeve. They come with a gland. They are all-in-one units. They are fully assembled and tested at the factory. Their axial location is already preset. So all you have to do with a cartridge seal is put it on the shaft, build your pump to its specs, tighten down the seal gland to its desired torque settings, lock the lock the sleeve to the shaft, remove the setting devices, and it's all set, ready to go. This greatly saves on installation time. It greatly saves on any types of mistakes that can be made, and it greatly increases in reliability. This is another variation of a cartridge design in a dual orientation. Remember that dual seals require an auxiliary system, so you have to have a barrier fluid in and out. And it's simply just two mechanical seals, one inside, one outside. In conclusion, mechanical seals can offer effective sealing for many forms of rotating equipment, not only centrifugal pumps. Mechanical seals are used in steam turbines. They're used on compressors. They're used in vessels, on mixing shafts. There are many different types of mechanical seals, and are available for appropriate types and must be selected for the given application. Depending on what you're pumping, mixing, driving, you have to sit down and make sure that you have the metallurgy right on the seal, the proper balance profile to make sure that you have proper lubrication. You may have to make sure that you have the proper selection of the seal flush. All of these things are done by the application engineer. You want to make sure that they're all addressed. Mechanical seals, of course, are a major factor in rotating equipment reliability. Again, the mechanical seal is like the weak link in the system. If you have seal failures, generally there's something that's causing those seal failures. Again, operational, mechanical, some sort of problem. As I was once told when I first got into the mechanical seal world, they don't like to commit suicide. So there's always something that causes the failures. Generally, if you identify a mechanical seal failure, understand what's causing the problem, you'll actually be able to backtrack and find other problems in your system that would eventually cause other problems, like bearing failures or even impeller wear. Mechanical seal reliability is affected by design and by the operational environments. Auxiliary systems are often required to provide an acceptable operating environment for a mechanical seal. In reference to the dual seal systems, require auxiliary systems. Sometimes you have pump applications that they cannot get outside that pump. You might have a rather large pump where you couldn't use a sealless pump design. You have to have a mechanical seal. In those types of systems, you want to have a barrier fluid, and that fluid can then act as a buffer. It acts as a collection area, so that in case you do have a failure, it will not spill out into the environment. That concludes today's session. If you have any questions, I think you can write them in here into the question box, and I'll do my best to answer them.
Okay, there is a question that we got up, and it said, what is the advantage of using mechanical seals over a sealless mag drive system?
Those
Could you restate that?
Yes. Mag drive systems basically eliminate the use of a mechanical seal. The problem with mag drives is they're limited by size and horsepower. I'm not exactly sure how big they make a mag drive up to, but generally on larger pumps, let's say big barrel pumps that may have 14 or 15-inch suction and discharges at high pressure, you can't have a mag drive in that situation. You have to have a mechanical seal. But on, let's say, a perfect example of a place where you would use a sealless pump would be something like hydrofluoric acid, which is very, very nasty stuff. It is used in some of the refinery processes, and that you definitely don't want to get on anybody. So in a situation like that, if it was the application was small enough, you would use a mag drive. But mag drives as opposed to mechanical seals, you definitely want to use a mag drive in anything that's very, very, very toxic material that you do not want to get out. Also, of course, a mag drive does eliminate the use of a mechanical seal, so you would eventually eliminate that potential problem. Again, mag drives are a little bit more, they're more expensive pump to buy, and they're not, they're not everywhere. And sometimes your plant manager won't let you take out a perfectly good pump to put in a mag drive, which may be 3 or 4 times the expense. I hope that answers your question. Any other questions?
Right now, that looks like that's all the questions. If you have any more questions that you would like to ask Frank, you can, if you want to direct them to my email, Sherry McNamara, S.McNamara, since you already have all that. I can forward them on to Frank, and we can get you the answer that you need.
Actually, there's one just came up here. I've been told that mechanical seals can drip when the pump is not running. Is this true, or is it a poor seal design? Interesting. Depending on the type of application, some mechanical seals are designed to drip. Those seals that are designed to drip generally are done because they can't fit, let's say, like a dual seal in the application, so they have to use a single seal. Say they're spinning the pump very fast, over 3,600 RPMs. You have to have additional leakage. That additional leakage is in the form of a drip. When they're shut down, generally they should not drip. Under load, like I just under running conditions, like I just explained, then you may see a drip. But those drips are generally within, one drip every 2 to 3 seconds to show you, to give you an idea for a rate. But if you have any drips that are on a shutdown system, there's probably something wrong. Generally, when the seal shuts down, or when the pump shuts down and the seals have a time to close together, they shouldn't drip.
Okay, there is one more question.
Yeah, it looks like there are any. Are there any standards for allowable strains, forces, and movements on a pump? That would depend on the type of frame that you have, pump frame that you would have. I would venture a guess. Basically, if you were to build a pump in your shop, build it, bring it out to the skid, bolt it into place, do your alignment on your from your motor, your coupling alignment from your motor to your pump. Then put the pipes together, and again, if you have to use come-alongs to straighten out the pipe runs to get them to bolt in place, if you do that, bolt them in, go back and take that coupler off, and do another laser alignment, there's a possibility that you could be out of alignment. If, let's say, you imparted a pipe strain in it, you took off that coupler, and there wasn't a misalignment, then that would be an acceptable amount of pipe strain in the system. But all the pipe strain would be there's no standard that I know of. It would be a function of how big the actual how big the pump frame actually is, and how well is it grounded and bolted down to the base. Any other questions here? God, I wish it. Trying to see, my display screen is kind of limited here. I'm trying to go through them. See if there's anything else here. Okay, looks like that was the last one on the list. Again, if anybody would like to contact me or talk a little bit more about ceiling systems, I can be reached at my office at area code 518-703-5381, or you can email me at frotello@seawertequipment.com. My name is spelled F-R-O-T-E-L-L-O at seawertequipment.com. Thank you, everyone, for attending. I appreciate your time. Have a good day.